Okay. Hi, everybody. May I ask to turn on your camera, please? You cannot hear me? I presume you should.
We can hear you now.
Okay, great, thanks. Okay, let's start. Today the plan is to continue pipeline, mainly discussing the issues that we face typically in pipelining at the microarchitecture level, and then having some discussion around this today, hopefully. And one announcement. So the midterm and I presume homework 3 already are graded. I asked TA to send you an email and releasing the grades. So as soon as he finds some time, he will do that soon, hopefully later today. Do you have any question for me before we start?
Do you know what the average for the midterm was?
Yes, I looked at it. It was quite high. I was happy. Let me again look at it to say what exactly it was. Yeah, actually the median was 83.5, which is good enough. There were some low grade, few of you. One of you had a relatively low grade, but there is still time for getting better grade overall, and there is no reason to be worried about grades. I was myself a little bit worried, but looking at these midterm grades, I'm happy to see that clearly I see improvement. So that's a good news. Any other question?
Yeah. Do you know how many more like assignments we have and stuff for the semester?
We have only this week and next week, right?
Yeah.
So I plan to have another assignment, so you can complete it before final. So there will be only one more assignment, or depending on the time, maybe two. But at least one you will have. And then for the final, basically, again, I would like to emphasize it. I would like to see that you clearly read the materials, hopefully the textbook as well. That would be helpful. And let us know if you can help in any way. I'm hoping that you get overall a very good, fantastic grade for this course. And one more thing, please. I presume they already released that, and you can evaluate the course. Make sure you log into Blackboard and do your anonymous evaluation of the course. That would be helpful for me to see where we are, and hopefully for the future version of this course, I can make any adjustment if needed. Okay, so if you remember pipelining, there were several issues with respect to pipelining, and you remember we discussed that we do not get these important properties that we want to have for the microarchitecture, these identical operations. We have different instruction, not all meet the same stages. As you remember, we have example of these uniform sub-operations. We have different pipeline stages, but not all of them require or have the same latency due to different characteristics that they have. Memory access versus ALU operation. And this will result in some internal fragmentation as opposed to the first one, which result in external fragmentation. And the last one is this independent operation. Dependencies between operations, as you know, and we will elaborate on that. I will elaborate on this today. So we need to resolve, first detect these interdependencies and resolve them if possible. But again, it is important to get the semantic correctly. We want to have the correct semantic after executing the program, right? So again, everything is possible at the microarchitecture. We were able to, do some crazy thing, like reorder some instructions if needed, as long as we make sure that we do not change the semantic, we do not violate the semantic of the program that we are executing. But we have this flexibility of, like, say, moving instruction and so on, and any other changes that we can make this situation better. We can resolve some of these issues. And this is related to pipeline stalls. Or on the other hand, with other wording is that when your pipeline is stuck somewhere, is not moving perfectly. So we call it pipeline stalls. So we want to balance the work in pipeline stages, like how many stages and what is done at each stage is the key thing that we need to figure out. And also we need to make sure that pipeline is correct, moving and full, but this is again ideal. We want to get as close as possible to this situation, not that is possible to get to this perfect situation for programs and execution. So we need to handle the dependencies. We have data dependencies and control dependencies. We have some resource contention. So many different instructions may need the same resource that we have. So we need to handle this contention of limited resources that we have. Obviously, we discussed, we had an example, we could add resources if that could help, but cost is involved, overhead is involved, and so on. And we need to handle long latency operations, specifically if they need multiple cycle for executing, like, say, memory access, for example. And we need to handle exception. Or in other word, the goal, the key goal we want to achieve is to improve throughput, and throughput means that the number of tasks that is being done by the pipeline at a unit of time. So this is the definition of a throughput. Or in other words, you want to minimize the stalls. So minimizing the stalls is equal to improving or increasing the throughput of the architecture of the machine. Is there any question about this? Are this clear? Very good. So let's talk about causes of stalls. You know that stall condition when the pipeline stop moving, anything that contribute to this, that stops or delay moving of the pipeline, meaning that execution of an instruction due to some dependency cannot be done because it needs to wait, for example, say. And we'll discuss some particular examples due to all of these reasons, either resource contention, dependency, or multi-cycle operations. But let's talk about dependencies first. These are interesting causes of a stall in pipelines, and understanding it, and also understanding the possible solution, because for resolving this dependency, it's not the case that we only have one solution. We have several alternatives for this, and I would like you to understand these in details. And basically, dependencies dependency between different instructions might have a different form, as we discussed, right? So at the high level, we have data dependencies and control dependencies, right? We have another category, which is resource dependency, or we call it resource contention, is the same. And we treat this separately due to some fundamental reasons. But for now, let's, I would like to mainly discuss about data dependencies. That's more interesting, but resource contention or resource dependency are basically easier to resolve, right? And there might be some solution for it, right? One solution is to eliminate the cause of contention. That's the easiest and the most straightforward solution for doing that, because we discussed we could duplicate the resources. This would result in an increase in throughput. So one example could be we use separate instruction and data memories, right? So we could use cache, for example, in this case. For example, if we want to write to a memory, right? We could have a cache in between. Instruction could write to caches, and then the cache would dump the values into memory whenever it's needed, right? So, but for caches are again new resource that we need to add. So we need to increase these resources. Again, cost and overhead are the other aspect that determine this trade-off. We could also have multiple ports for writing into the memory. If we have one port, obviously for write, this means that one instruction could write to the memory. But if we have two ports at the same time, if you have two ports, two instructions could write to the memory at the same time. 3 ports, 3 instructions, right? So we could increase the number of ports of the memory unit. But again, adding port, meaning that you need to change your memory unit, you need to, and adding extra ports, meaning that you increase the cost. So adding a port is not trivial, right? And there would be a need for changing the memory unit. But these example, as you see, is you don't need to think hard. It's pay the cost, get this resolve, and increase the throughput, right? So this is the first solution. The second solution is that you can detect the resource contention, right? And basically, and this detection could happen ahead of time based on analysis of the program that you could do, is that you can detect, okay, like these two instructions or these multiple instructions need the same resource at the same time based on the program analysis that you do. And this, with the instruction analysis over the instruction in your program, you can figure out ahead of time, okay, when a contention will happen in the future, and then you can do all of these possible variation, like stalling one of the contending stages, right? But the question is that, okay, like what stage we want to stall, right? What stage we want to stop moving to give us a better or a higher throughput, right? Whether we want to stall later stages, writing back to the memory type of thing, or accessing memory, or we want to stall fetching a stage, right? There are some trade-off of deciding which stage we want to stall, which affect performance, right? Affect throughput, and again, there are possible alternatives for this, right? Example is that what if you had a single read and write port for the register file, right? Let me. This is a good example, for example, for this case, right? So you have a program that has 4 instructions, and you see the overall timeline, right, from 1 to 8 in this case, and each have different stages, right? 5 different stages. So the first instruction is adding S2 to S3, storing the result in S0. And you already see that the next instruction and depends on S0 because it uses S0 in one of its operand and add it to S1 and store the result in T0. So there is a dependency here between this instruction and previous instruction add, right? Let's see where else. Here in the third instruction, you also use S0, right? So the third instruction also depends on the first one, and also the last instruction. You see S0 there as well. So the next 3 instructions all depends on the result of the first instruction, right? And actually the result will be written to S0, as you know, if you look at the pipeline. So you need to first fetch it, decode it, do the ALU operation, memory access, right? In this case, memory access, this instruction do not do anything, but it needs to go through memory access, right? And then writing back the result to register file, right? Once this writing back result to S0 happen, all other instruction can rely on the value because of these dependencies, right? So you see that the second instruction, it starts from time 2, right, T2. And here in the second stage, it reads from this register value. So it requires the value of S0. It retrieves the value of S0 at the second stage of the second instruction, right? And you see that in the timeline is at T3, right? So this means that if we rely on this dependency, we need to install this instruction. Also the third instruction, because it requires the value of S0 at T4, right? The last instruction, subtraction, it requires the value of 0 in the same timeline, right? T5. Definitely, we need to. I mean, if stalling is one way we want to go, we'll discuss some alternative. We need to install these two and or, right? The second and the third instruction. The last instruction, since it requires at the same timeline, right? At the same time, and if read and write, you could do that during the same time, the same cycle time, right? So, for example, you can say, hey, I read first during the first half of the cycle, and during the second half, I do my writes, right? Or the other way around, or however you would like. If you could do this, then maybe you are able to execute the last one without stalling it. But But if you don't have this, then you also need to wait for the next cycle to execute this task, and you need to install all 3 following instructions, right? Is that clear for you? Is this example clear? Because understanding this is fundamental for understanding the following concept we will discuss. So it's a very simple program, 4 instructions, different type of instruction, and there is clear dependency between all these 3 follow-up instruction and the first instruction that got into the pipeline. And you clearly see the issues that we previously discussed, right? So add doesn't need any memory access, but it will go through and it wastes 1 cycle for memory access, right? So this is an example of it. Right. Let's also discuss some other, maybe at least contemplate about like some other possible scenario or some other alternative solution for fixing this. Here you see that like the first instruction, when it's going through these stages, you have the result here at T3, right? So after the add operation is executed in ALU, you have the result by the end of T3, right? Once this ALU operation has been done and has been finished. So by the end of the cycle, by the end of T3, you have the result. The first instruction, do nothing in the 4th, right? And in the 5th, you just simply write to the memory. But you have the result in T3. So if you find a way to forward the value of this operation, whatever you want to write to S0, forward it to instructions when they needed it. Say, for example, you can, here you need the value of S0. Technically, you need these values at T4 for AND. The second one, you see that this AND operation happens at T0. ALU is the resource that requires the value of S0 and S1. And if you find a way to forward this result, right? So by the end of T3, you already have this result. And if you forward that directly into this second instruction, the 4th stage of the second instruction, then this instruction can move forward without ever needing to stall the instruction. The same is true for the 3rd and the last instruction. If you are able to find a way to forward these values whenever it's produced, and you clearly see that the value of S0, whatever you wanted to write to S0, right, is produced at T3 here, meaning that it's ready to be used with other instructions. This is one way you can think about it. We will also discuss some other alternative approaches, right? But stalling instruction is not the only solution. There are other possible ways. If we want, we can do that. And again, even adding this, meaning that we need to add some data path, right, at the microarchitecture to pass the result between like ALU operation for like from here to here, right? And that this means that again, extra cost, overhead needs to be paid back, and there is always a trade-off space here. And regarding the last instruction, as I mentioned, so you could figure out writing. Say you first write in the first half of the cycle and read in the second half of the cycle. And then, like if you do that for this example, here you are ensured, guaranteed to read the correct value of S0 after it has been written by the first instruction, right? And this is the semantic that you want to get, at least in this example, right? Doesn't mean that all the time you want to have this property. Sometimes you want to read a value before somebody else writes this value, because you already have the right value in the register, in the memory that you want to read. So preserving this semantic is really important. But for this scenario, if we are able to have this assumption, if we are guaranteed to have this assumption, writing take place in the first half of the cycle and reading the second half, then this is the last instruction is good. Yeah. So let's talk about possible type of data dependencies. So we have specifically 3 types of data dependency. The first one is flow dependence, which is a true data dependency. That the other 2 is not, they are not true data dependence, as we'll discuss. But the first one is, and happens most of the time in your program, that you need to read a value from a memory after it's been written, right? Let's have right away an example to discuss this, right? So the first one, here we have R1 up R2, say like R1 add R2, doesn't matter what this operation is. We write it to R3, again, these are registers. And then right after, we have R3 as a part of this operation, this instruction, and the result will be written to R5, right? So you see clear dependency between these 2 through R3. So the first one writing to the R3 to this individual register, and the second one reading from it, right? So read after a write has happened, or raw, read after write. This is an example of flow dependency. Output dependency is the scenario where write happen after a write. Here, this one, the last one, the output dependency. So here, the first instruction, adding, basically doing operation between R1 and R2 and write the result to R3. The second, using R3 and R4 writing back to R5. The third one is again doing using two other registers, R6 and R7, but writing back the result to the same registers, R3. So here we have a situation where two different instructions using the same resource, writing back to the same register. Okay, and think about it. Here, I mean, forget about this second instruction. Between first and the third, from semantic point of view, there is no real dependencies between these two instructions. It doesn't mean that the third instruction requires something from the first one. This dependency is not, and that's why we call it is not a real dependency, right? It's just happened that these two instructions using the same resource, writing back to the same resource, which may introduce some incorrect execution, incorrect, something may go wrong as a result if this dependency is not taken care of. Why? Maybe we need this R3 somewhere, right? Say an instruction after the third one, which really requires the value of R3 after only the first instruction, right? Say that we need a value of R3 somewhere here, but we don't want this operation to write the result to R3 before we use the value of R3 that has been produced in the first place, right? This may result into some inconsistent value or inconsistent execution or incorrect execution of the program as a result. May not, may, right? And that's why it is not a real dependency. This just happened that they use the same register. They could use totally different registers, right? So one solution is that, hey, like there is no true dependency between these two. We could change R3 in the second instruction to R10, say, right? So if we find an alternative register to write the result of the third operation, third instruction into, then we are good to go in this example, right? We did not violate any semantic of the program, right, as a result. So changing the register name in this case is one solution that can resolve this output dependency, which otherwise may create some incorrect result. Is this clear, the output dependence? It's using same resources, just but there is no semantical dependency. There is no dependency in the program that, for example, the second instruction may need the value of the first. So it's different from the flow dependency. The third one, anti-dependency, is the case when write happen after a read. So you see in the middle anti-dependence. So here we use R1 and R2 to write the result to R3. And then after we read, we write back and to R1 another value, right? So write happens after read. And this clearly created another type of dependency or anti-dependence between these two instructions. Which in this case, if this ordering was consistent with the semantic of the program, I mean, this ordering could or could not create any inconsistent result, right? This doesn't mean that all of these dependency will introduce inconsistent or incorrect result, but depends on the semantic of the program which is executing on the machine. But these are like possible type of dependency, data dependencies that may happen. So which ones cause the stall in the pipeline machine? As we discussed, maybe all of them, all of these dependency, if they result in, if not taking care of it, would result in incorrect execution, then all of this situation, we may need to stall the machine in order to make sure that semantic is preserved during the execution. Definitely the flow dependency is the one that needs to taken care of it all the time. If there is a true dependency, we have to have mechanism so the correct ordering happens and the correct semantic is preserved. Anti and output dependency, like for them, as we discussed, we could simply, if not taking care of it is easy, we could add, we could change, like for example here we could change R3 to like R10, right? So adding a new resource, changing the name would resolve this dependency, and there, after changing this to R10, there wouldn't be any dependency between these two, right? So they become independent as a result, right? Currently, you see that they are dependent. In this case, output dependent, and anti-dependent also they're dependent. But if you change these, like in this case, if you change R1 to say like R10, then there wouldn't be any dependency between these two instructions. So one easy solution is to change the name of the register, because they are dependent based on the name, not the actual value that will be written or will be read from these register files. Is there any question about this? Is that all clear? Okay. And this example, we had that, right? So we have a load word here, which the instruction is fetched, during the first clock cycle. The second clock cycle, the new instruction comes to the pipeline. First instruction moves to the second stage, instruction decoding, and so on. So then in the third clock cycle, sub moves to the instruction decoding and load word to the execution, and then as you see, all the way back until here at this stage, load word is finishing its work. So the next cycle, cycle 6, there wouldn't be any load word. It's already been done fully, and sub needs to write back the result to register, and then in clock 7, pipeline is cleared. In this case, as you see, in this case, as you see, there is no dependencies between load word and sub. Load word is, as you know, is loading the content of a memory into a register, writing it back to register number 10, and sub is not using register number 10 at all, and doing a subtraction between register 2 and 3 and writing the result back to 11, and there is no dependency between these two at all. So we do not need to worry about it. But in the examples that we have, there are situations that we need to handle this data dependency explicitly. So we need to figure out solution for handling these possible data dependencies, like flow dependency, output dependency, anti-dependency. If you're interested, you can take a look at this important paper talking about data dependency between in a special type of microarchitecture called superscalar processors. Superscalar is also an important topic in computer architecture. We don't have time to talk about it, but it is typically not taught in these basic courses. In more advanced computer architecture type of courses will be taught. And it talks about like several things, including pipelining stuff, but also like out of order execution as well. So it's a long paper. And there are different solutions for handling data dependency that we need to talk now to see how they can handle flow dependencies, right? This important type of data dependency, because as you know, they're more interesting. For anti and output dependency, easy solution exists. Just changing the name of the register would work, or maybe writing to the destination in one stage, and then this would not create any semantical issues with the program execution. But things could go wrong if if we do not obey that, right? And things could go wrong, really. I'm talking about the first one. If we want to write to the destination in one stage, for example, the case where we change the order of instructions, and actually there is an important concept, out of order execution, which if we get time, probably we do not, is important. Again, a strategy to improve performance for machines, which rely on changing the order of instruction, but obviously based on some strategy that we make sure that the semantic of the program is not violated, so we get the correct result. But let's focus for now on only flow dependencies and see what are the possible solutions for this. The first one, detect and wait, is easy, right? Easy solution, meaning that we could detect these dependencies ahead of time, so we can stop any instruction from execution until we have the value in the register file, right? So in the examples that we had, so here we had this scenario, right? So the first solution talking about the case where we stop all of these dependent instructions until we make sure that the value of S0 has been written back to register file, so we can resume the execution of the following instruction. This is easy if we predict this dependency, which we could, but it's not ideal because this would result all other instruction stop until T5, right? And after T5, they can continue executing. So this would result in delay, and the throughput will be decreased as a result. But this is easy to implement, right? So the only thing we need to do is to detect dependency and stop some instruction from execution if they are dependent, and resume them once the value has been written into a register file. So that's the first strategy, which is easy but not ideal. The second one is what we have discussed, right? So we could detect similar way. We could detect when a data dependency happens between instructions, and we could forward the value as soon as the value has been produced, right? So in this example that we had here, we don't need to really wait until this stage. As we discussed, the value has been produced at T3 in cycle 3. We didn't have the value in cycle 2 and cycle 1, right? As you you clearly see. But in cycle 3, at the end of cycle 3, once the ALU operation has been executed, we have the result that we expected to have. We could simply forward this value to the execution stage of the second instruction, and so on, right? And also for the third and for the last one. So once the value has been produced, but again, to emphasize, the value is produced in the third cycle of the first instruction, not before that. So that's the second one. The third strategy is detecting and eliminating the dependence at the software level. You know that the compiler could detect this dependency, right? And the compiler could do some interesting intervention to the program. Let me maybe use this to discuss particular example that may be more helpful rather than. You also see this as a black screen? Or it's just me? Can you confirm what you see?
No, I see
It's
a
black.
black screen.
What's wrong? That's strange. Why it doesn't work? That's absolutely strange. Maybe using the different. Okay. Let's have an example about this. So imagine that we have multiple instruction in your program, and the compiler is able to somehow use the semantic of the instruction and also the structure of your program in order to reorder instructions in order to help improving the throughput, increasing the throughput, right? Without ever needing to add any hardware, new hardware resources in order to take care of this dependency, right? So imagine that you want to do, like, let's say R1 operation R2, and then writing to R3, right? And then you use R3 operation R4, doing to R5, right? And you have, say, you want to use R5 operation to R6, R7, right? So you see the dependency between these two, and also these two, right? So explicitly, this dependency between R3 in the first and second, and R5 between second and third, you see this already, right? And the compiler can detect this dependency based on their numerous various different techniques at the software level, where the compiler can exploit not only the semantic of the instruction, but also the structure of the program. Because like in your program, you have some structures, right? You have if statement, you have like while loop, you have all sort of construct that determine the execution of a program, right? So it's not the case that all your programs are linear, right? No, you have some if that determine where your program is going. Like you have maybe some linear, and then you have some joining, right? And then you might have some other stuff, right? Again, this may also, you have some scenario where you use case construct, right? And this may result in some even very complex execution, right? So you have some structure in the program, and the compiler is able to detect or to construct this structure, right? You will learn about these program analysis stuff for basically doing all sort of program analysis, right? Detecting dependencies, one goal you want to achieve with program analysis, which is useful in this case. So compiler can easily detect the dependency between all sort of these instructions. And then once the compiler knows about this dependency, it can reorder things. One example could be, hey, we might have later on, right? We might have some instruction like let's say R10, then we have R9 operation with R11, right? Something like that. So you already see that this instruction has nothing to do with this. There's no dependency between this instruction and these three instructions above, right? So it can reorder things. Say maybe here I have this dependency, so I need to, if I don't do any reordering, if I do not do anything, The only thing that I can do is to stall this instruction and also this one, delay things while I'm producing R3, the value of R3, which obviously we do not want to have that because this would decrease the throughput a lot. And we have to, at the end, eventually, we have to execute this operation, this independent operation. Maybe we could, like, instead of waiting, doing nothing here in between, we could execute this instruction here, right? And like by executing this instruction earlier than later, we did not violate any semantic of the program, but we did violate one thing. We did violate actually one fundamental property that we have discussed many times. Can one of you mention what would be that property that we are violating? It's very easy. Did you understand the question? Do you want me to repeat the question, or you're thinking? No, you're muted.
Yeah, I was muted on my end. If you could repeat it, that would be great.
Sure. The question is that we discussed about this scenario where we want to move this independent instruction in between here in order to do something, in order to not waste the cycle, the resources by doing nothing, because there's no dependency between here and like the first instruction, so we could execute it in between. My question was that, yes, since there is no dependency between this and that, we do not violate the semantic of the program, but we do violate one thing, one property of the machine that we discuss extensively. And I ask, what is that property I'm talking about?
Would it be we talked about write before read earlier, and we can tell that we're doing that here.
No, I'm talking about one other property, not about this dependency, which basically, if you remember, one of the property of one Newman machine was sequential program execution, right? But so the instructions are executed sequentially, one by one. There was no, so basically, there was not parallel execution or executing, instruction out of the order that has been written in the memory, right?
Right. So that makes sense then. I guess if we move that instruction, we leave the von Neumann architecture and we move to something else.
Yeah, exactly. And we clearly violated this. But again, remember, so this violation happened at the microarchitecture level, right? So you remember, like we discussed, that yes, as long as we do not violate anything above the ISA level, we are fine. So we have these properties that we wanted to achieve, like one instruction at a time, right? And basically this von Neumann model, but below ISA at the microarchitecture, we could do all sorts of things. We could violate these properties as long as we do not make any changes that the programmer needs to be aware of, right? So these changes, programmer doesn't need to be aware of it, of this change, because we do not violate any semantic of the program. So like programmer doesn't need to know like, hey, like we executed this instruction out of the order. Fine, if you do not make any, trouble for me, then do all sort of this, right?
It feels really weird to do that though, because we talked about it as the von Neumann architecture. I feel like that would better be phrased as like a von Neumann style ISA would be a better name for that. Because if we're modifying the microarchitecture, then that fundamentally is not an architecture anymore. We've changed it to a different type.
That's right. So these are like, you can think about these as ideas that improve performance or give you additional benefit, right? And basically while preserving, while not enforcing programmers to do something differently, right? Or having guarantee that there wouldn't be any violation of the current semantic of the program, right? As long as we have these guarantees, and there are numerous type of these violations which have these guarantees of like preserving, not making any changes at the ISA level and so on. These are like tricks or like ideas that could improve performance or decrease cost, and basically make some, give us some benefit, but again, this means that some of these really violating the properties of the von Neumann model in one way or another.
So a question based on that as well then. So if we start expecting the programmer to understand these rules and have to implement them in the program, that we would leave the von Neumann architecture and move to something else. Are there any like microarchitectures that specifically move away from this and like talk about what we have here, where we can move instructions around like this? And the programmer has to be the one who does that?
Can you repeat your question? I didn't understand it.
Are there like types of microarchitecture where this behavior is not automated by the microarchitecture itself? Is there like some alternative to the von Neumann style where the programmer is one who says, if you can do this instruction here instead, do it? Or is there some alternative?
Alternative which enforces the programmer to be aware of these changes?
Yes.
Well, I mean, like we could, but again, this would, we don't want to do such thing that the programmer is aware of this thing, because hiding such variation from the programmer, meaning that the programmer doesn't need to know and does write the program the same way, no matter on what architecture this program is going to run, right? That's the portability benefit that they get, right? If we give such information to the programmers, meaning that we create a dependency between the machine and the program, this program only needs to execute on this particular machine. But we want to increase the portability, and that's why like these ideas should be hidden or not affecting the the ISA in this way. But
Okay.
obviously, we could, if we want, we could communicate these things and make some variation and make it architecturally visible, but that's not a good idea, you know.
Okay, so that kind of solidifies for me now. I kind of understand the difference between a microarchitecture guy versus a programmer. The microarchitecture guy is the one who, their job is to make it so the programmer's job is the same regardless.
Exactly. Or on the other hand, like you can think about it as different instantiation or implementation or realization of the same thing, right? Of the ISA, the same ISA, differently, right? But from the program perspective, it doesn't matter whether this program is running on this microarchitecture I, right? 1 or 2 or like 10, right? So it doesn't really matter as long as all of them basically are implementing MIPS. So in one, you could have like maybe you want to install no variation of the instruction in the program. The throughput is like maybe not that great, right? And you stick to the whole property of one Newman stuff. In 2, maybe you want to implement like one of these strategies that we discussed, maybe forwarding the value once it's produced. The same way, doesn't matter, right? And all sort of other alternative, right? These alternative implementation of the same ISA would give the portability, so the program would produce exactly the same result in all different implementation, no matter what, exactly the same result, right? But with different performance, with different cost. But the result should be precisely the same for any type of program if it gets executed in either of these microarchitecture or different implementation of the same architecture. But that was a good question, right? I'm happy you asked it. And now it is clear for you. So again, the key idea here is to reorder things, to put the to put some other instruction, as long as they don't have any dependency, to fill the gap between these instructions that needs to be weighted otherwise. So we want to somehow use the resources by reordering things, make the best use of resources or increase the utilization of the resources by reordering instruction. And this is again compiler job. Compiler does this for us. This is hardware. We don't want to do this at the hardware level. So this is an alternative that enable basically this at the software level. So that was the third strategy. There are some other alternatives, like predicting the value of a variable you use and executing speculatively, right? So in the example, like in this example, you may want to like guess in order to like, instead of like using the actual value, you want to guess what would be the value of S0 and rely on this guess to execute AND, right? Obviously, with any guess, there would be some, you know, bad prediction or incorrect prediction. Then if you are able to adjust for any mistakes that you have made, then and ensure that the semantic of the program is preserved, then why not, right? So you get reward as a result of good prediction. So you don't need to do additional thing if your prediction was correct and you executed the instruction based on this prediction. You don't need to do any adjustment for the value that has been produced, and you're good. But you need to verify that whether like this later on, whether this prediction was correct or not. You could do some like multi-threading, right? You could do something else whenever needed. So you don't even need to detect the dependencies as a result. So whenever you need to install, you can do multi-threading. Let's stop here. Then we'll talk about interlocking later on, and some other approaches for detecting dependencies, and how we can take care of this. But these are like important. Detecting and having some solution for increasing throughput was the key idea that we discussed today, right? So it is important to understand these data dependencies and alternative dependencies that we discussed briefly, and having an idea about possible potential solution. And the solution that we have discussed, if you think about it, they have different flavors. Some of them can and should be implemented at the hardware level, like forward the value. Some of them you should do it at the compiler or software level. So software can clearly help with like eliminating the dependency at the software level, or like identifying or reordering instruction if needed. But for the hardware, either is impossible or very, very costly. And to the extent even you can rely on prediction as well. So they should give you some ideas like about the flavors of possible solution. Each of these, and again, think about it, like each of these, I gave you an example, would result in different microarchitecture, right? And has been used in different microarchitecture, these ideas, actual microarchitectures, right? And like depending on the type of program, the kind of situation that you execute, one strategy might be better than the other. Okay, I stay here for a few minutes. If you have any question, I'm happy to answer.
Thank you.
Thank you.